the direction of magnetic field will be like this. So this is how we can find the direction of magnetic field. Now, what is magnetic field density? Friends, we saw the magnetic field density, electric field density. Now we are going to see magnetic field density. So the magnetic field density is defined as the flux per unit area at right angles to the flux. Friends, in last lecture we saw that the electric field density is the electric flux per unit area. Same in the magnetic field density is given by the magnetic flux per unit area. And the magnetic field density is denoted as B. Here we have an equation. B is equal to phi by A Weber per meter square. It means the magnetic flux density is equal to the magnetic flux phi by the area. The unit of phi is Weber and the unit of area is meter square, so that we can have a unit of magnetic field density Weber per meter square. And we have another unit which is known as Tesla. So we can say that the magnetic field density is phi by A Weber per meter square or phi by A Tesla. Now what is magnetic field intensity? Magnetic field intensity is defined as the magnetomotive force per unit length of the magnetic flux path, and it is denoted as H. Same in electrical field, we saw in last lecture electric field intensity. Here we can see that the magnetic field density is equal to H is equal to Ni by L, where N is the number of turns which is wound around a coil, I is the current and L is the length. So that we can say that the unit of magnetic field intensity is equal to ampere turns per meter. The number of turns are measured in turns, the current is measured in ampere and the length is measured in meter. So we can conclude that the unit of H is Ni by L, ampere turns per meter. Now what is the relation between magnetic field density and magnetic field intensity? The magnetic field density that is produced in any material is found to be directly proportional to the magnetic force H, or we can say that it is directly proportional to the magnetic intensity H. Thus, if the magnetic intensity will be greater, then the magnetic density will also be greater, and if the magnetic intensity is less, then the magnetic density in magnetic circuit will be less. Here we can see that B is directly proportional to H. Now here we can again put a constant, B is equal to mu into H, and then we can say that B by H is equal to mu, which is permeability. The BH ratio in any material is a constant which is equal to the absolute permeability of the material. And in place of mu, we can put mu 0 into mu r, so that we can say that B is equal to mu 0 into mu r into H. Now friends, what is reluctance? In electric field, we saw resistance. Resistance is there in the electric field which opposes the flow of current. So in the magnetic field, the reluctance is same like resistance. The reluctance will oppose the magnetic flux. See that the magnetic flux cannot be passed, but it is produced in the magnetic circuit. So the reluctance will oppose the magnetic flux to be produced in any magnetic circuit. It means that if the reluctance is more in magnetic circuit, then it will produce low magnetic flux. Here we can see that the property of the material that opposes the production of magnetic flux through it is called reluctance. Reluctance is basically denoted as S. In electric field, we have resistance R is equal to EMF by flux. Here we can say that the reluctance S is equal to MMF by flux. It means the reluctance is equal to magnetomotive force by magnetic flux. Magnetomotive force is given by N into I, which is number of turns into the current, and flux is given by phi. So we can say that S is equal to Ni by phi. Here we have another equation, S is equal to L by mu 0 into mu R into A. So that we can say that the reluctance is depends upon the length of magnetic circuit, area of magnetic circuit, and relative permeability of magnet. Here length is given as length, L is given as length of the circuit, A is given as area of the circuit, mu R is the relative permeability, and mu 0 is the permeability of air. Now friends, we can see how the formula L by mu 0 mu R into A is derived. So here we can see that S is equal to Ni by phi. We know that the magnetic field intensity H is equal to Ni by L. So we can say that N into I is equal to H into L. Then we know that the magnetic field density B is equal to phi by A. So that we can find phi is equal to B into A. Putting the value of phi and Ni, we can find S is equal to Ni by phi, which is H into L by B into A. But we have a relation B is equal to mu 0 into mu R into H. So we can put S is equal to H into L by mu 0 mu R into A, because B is equal to mu 0 mu R into H, here H. So finally we can conclude that S is equal to L by mu 0 into mu R into A. So friends, this is reluctance. Now we have a magnetic circuit in which magnetic core is given, the area is given, and the current flows through the magnetic circuit. This is a simple magnetic circuit. Now if we have different materials, so what will be the total reluctance of that circuit? Here we have two materials. The first material is having the length L1, it is having the area A1, and the permeability of first material is mu1. Then in second material we have the length of the material L2, the area of the material A2, and the permeability of the material mu2. So that the total reluctance will be equal to the summation of these two reluctances. It means that S will be equal to L1 by mu1 into A1 plus L2 by mu2 into A2. Now friends, we can compare the electric circuit with magnetic circuit. There are many similarities between electric circuit and magnetic circuits. The first similarity is that in electric circuit the current flows through the electric circuit, but in magnetic circuit the magnetic flux does not flow, but it is produced in magnetic circuit. The second comparison is that EMF is required for the flow of current. EMF is known as electromotive force. You can say that voltage is also electromotive force. So voltage is required for the flow of current in electric circuit, but in the magnetic circuit we have to produce magnetic flux. So MMF is required for the production of magnetic flux in magnetic circuit. The full form of MMF is magnetomotive force. The third similarity is that permittivity allows more current to flow in electric circuit. It means that if the electric circuit is having more permittivity, then more current will flow through the circuit. And in magnetic circuit, if the permeability of magnetic material is more, then it will produce more flux. So here permittivity is there in electric circuit, same in magnetic circuit we have permeability. After that we can see resistance. As I said earlier that the resistance opposes the flow of current in electric circuit. But in magnetic circuit, the reluctance opposes the production of magnetic flux. After that we have a similarity, electric field density. Electric field density is equal to Q into A. It means the charge into the area, and the magnetic field density B is equal to phi into A. After that, electric field intensity. So electric field intensity is equal to F into Q. It means force into the charge. And in magnetic field we have magnetic field intensity H is equal to IN. The unit of current is ampere in electric circuit, and the unit of flux is Weber in magnetic circuit. So these are the comparison between electric circuit and magnetic circuit. It is frequently asked in the exam. Now based on the equations, we derived many equations, so based on that equations we will solve example. Here a beautiful example is given in which it says that a coil of 200 turns is uniformly wound around a wooden ring with a mean circumference of 600 mm and area of cross section of 500 mm square. It means number of turns is given as 200, length is given as 600 mm and area is given as 500 mm square. If the current flowing into the coil is 4 ampere, we have to calculate three things here. The first thing is magnetic field strength, which is H. The second thing is flux density, it is B. And the third thing is total flux, which is phi. Here number of turns are 200, length is 600 mm, which can be converted in meter as 600 into 10 raised to minus 3 meter. The area is given as 500 mm square, which can be converted in meter square as 500 into 10 raised to minus 6 meter square. The current flowing in this ring is 4 ampere, so I is equal to 4 ampere. This is our circuit in which the current flows, number of turns are there, length is there and area is there. Firstly, magnetic field strength. So we know that magnetic field strength H is equal to Ni by L. Putting the value of N 200, after that the current is 4 by 600 into 10 raised to minus 3. So putting these values, we have magnetic field strength H is equal to 1333 ampere turns per meter. Always remember the unit of these things. Secondly, we have to find flux density. So we have relation B is equal to mu 0 into H. So 4 into 10 raised to minus 7, which is the value of mu 0, and if we multiply it with magnetic field intensity H, we can find the magnetic field density is equal to 1675 Tesla. Finally, we have to find total flux. So the total flux is equal to phi is equal to B into A. We know that the value of B is 1675 into 10 raised to minus 6 and the area is given as 500 into 10 raised to minus 6. So that 0.8375 the total flux. Now friend, here is another example which says that a coil having 600 turns is wound uniformly over an iron ring whose mean diameter is 41 cm. Friends, here the diameter of coil is given. The relative permeability of iron is 1200. It means mu r is equal to 1200. If a current of 3.2 ampere flows through the coil, then find the flux density. It means we are given number of turns n, we are given the diameter, we are given the relative permeability, and the current is also given, and we have to find the flux density B. Firstly, we can say that the current through the coil is 3.2 ampere and the number of turns are 600. So the total MMF will be N into I, which is 600 into 3.2. So the total MMF will be 1920. After that, the mean diameter is given as 41 centimeter. We all know that the mean length of the iron ring is 2 pi into r. Here 2 into r, it means the diameter is given as 41 centimeter, or we can say that 0.41 meter. Mean length is pi into dm. So the magnetizing force H will be equal to Ni by L. Ni we found 1920 and the L is given as 0.41 meter into pi. So finally we can find the magnetizing force H is equal to 1490.62 ampere turns per meter. But we have to find the magnetic flux density. So here we derived a relation B is equal to mu 0 mu r into H. It means the density is equal to the permeability into intensity. We found that intensity is 1490.62. Putting the value of these three quantities, we can find the flux density, which is 2.248 Weber per meter square. So these are the two examples. Now we will see what is electromagnetic induction. Friends, before going to electromagnetic induction, we have to see what is electromagnet. So there is a difference between magnet and electromagnet. Here we can see difference between magnet and electromagnet. What is magnet? So magnet